All right, so the first thing that we are going to do is we are going to draw this diagram. Okay, let us draw this diagram first. Let us draw this diagram first. That diagram is what we are drawing. It's quite different from the other one, from the other experiment you have just seen, but I'm going to show you the reasons why. And the reason why we have a smaller capillary tube and a bigger capillary what? Tube. We are all drawing that diagram. Let us draw that diagram. Okay. Have you finished? Sean, have you finished?
Not yet.
No, for you, you do your things very fast, especially eating. Sean.
Yes, teacher.
Am I deceiving?
Yes, teacher, you're deceiving.
I don't think so. Beaker, water. Okay, so we are going to investigate, but let us first do that diagram. So finished. If you have not finished, you can see the one that I've drawn. So let us write the procedure. So we want to investigate the capillary rise in this tube. So what should we do? First of all, we shall write the reason to this, but let us write this, okay? We are going to, okay. So what is our procedure for this investigation? Number one, they are saying place water or pour water in a beaker. Pour water in a clean beaker. Halfway. Half full or halfway. Can say halfway, full stop. So you pour water in a beaker halfway. Then two, you place a capillary tube of a smaller size in a beaker containing water. So place capillary tube of smaller size in a beaker. So here they are saying place a capillary tube in water vertically, leave it for some time until the water is no longer rising, okay? So the next thing is to leave Leave the capillary tube for some time until no longer is rising. Leave the capillary tube for some time until no water is rising, until no water is rising. What are they saying here? That when you get this capillary tube of smaller size, dip it in that beaker containing water. Now what will happen is that the water will rise, and when it rises, it will reach at a certain point and it is stationary. So you note and mark the point, note and mark the level of water in a capillary tube. So that is the next thing, that to note and mark the level of water in a capillary tube. Okay. So the other step is to repeat the procedure, with another capillary tube of larger diameter. So now you use another capillary tube of another diameter. So what are you going to observe? What will be our observation? What will be the observation? And we are going to write also the explanation to our observation. So observation, if we have these two capillary tubes dipped in water like that, what is our observation? The observation, you are seeing it there in the diagram. That's the observation. In other words, they ask, what's the observation? The observation, you write what you see, full stop. And when they ask explanation, then you explain. If they ask, explain your observation, then you have to write the observation, then you explain the observation. Excuse me, but here we are going to write the observation first. So what is our observation? Now this one should come from you. You tell me, what do you observe? What is our observation when you dip those two capillary tubes? Ruben, say something before the cock crows. Ruben? Ruben?
Yes.
Yes, say something. So what do you observe? What is our observation here? Ruben?
Yes.
What is your observation here?
Teacher, a minute.
A minute? Who knows? You put up your hand if you know. Ruben is just wants us to waste some good time. Who knows? I want a girl first. A girl first? Who knows? I want a girl first. Catherine, yes? Catherine? What is your what do you observe here? What do you see here? This is the one of a larger diameter. This is the one of a bigger. Yes, Bridget.
Teacher, me what I observe is the water level in the larger tube is it's low, and the one in the smaller tube is
very
bigger
good.
than.
Very good, very good. The water level in the tube with a large diameter is lower than the water level in the tube with a smaller diameter. That is it. That's what we are seeing. That the level of a large diameter is low compared to the water level in a capillary tube of small diameter. That is okay. That's correct. Right? Water rises in both tubes, tubes, but the water level in a capillary tube of small diameter is higher than okay, let me zoom out, is higher than that of a larger diameter. It is true. That's what we observe. Thank you very much. How do they clap on Zoom? Let me see how they clap on Zoom. How do they clap on Zoom? Hey, thank you very much. Thank you very much, Bridget, for that. So that is correct. Now, who can give us the explanation? What's the explanation to that? Why does it rise in the smaller tube and why is it low in so what is our explanation? Actually, the answer is already here. What's the explanation? This time must be a boy to give us the answer. A boy to give us the answer. We have Ruben, we have Pav, there is Sean. Those are the boys. So you give us the answer. What's the explanation to our observation, to that observation? Why does it fall in a large diameter and why does it rise in a smaller diameter? Why? Hey, boys, Pav?
Yes, teacher.
Are you thinking?
I think the answer is because the smaller tube, I mean the narrow tube is having the smaller diameter, and so that's why the water level is high in it.
Yes. That is correct. Because the smaller tube has a small diameter and the water level rises higher than the tube with a larger diameter. That is correct. Now let me ask you the question. Let me ask you a question.
Yes.
Is it the same volume of water that rises in both capillary tubes?
No.
Pav, I have you now. Is it the same volume? I'm asking volume. Is it the same volume of water that rises in those tubes?
No.
Why?
Because the one with the bigger diameter is, since it's having the bigger diameter, much water will have to go into it, whereby the smaller one is where the small diameter is where it has to, the smaller amount of water will enter.
Okay. Now, Pav, let me give you this scenario, okay?
Yes.
I don't know whether you are seeing, this is my water bottle, okay? And I think you can see the level of water it is here, isn't it? Are we together? It is here.
Yes.
Okay. Now, if I pour this water in a water tank, these black ones that are outside, will that water level in that tank be the same with this one here? Will it be of the same height?
No.
No. But the volume of the water is the what?
The same.
Is
Yes,
the
I get
same.
it.
Okay. It's the same. So the thing is that these two capillary tubes, the volume of water that has risen is the same.
Same volume.
But since their diameters are different, the one with a smaller diameter, it has a high level of water compared to the one of a larger diameter. Have you understood that?
Yes.
So the reason is because of the diameter of those two capillary tubes. So the explanation there is that, say, water level in a smaller tube, is high because it has a smaller diameter compared to that of a bigger tube with a larger diameter. So water level in a smaller tube is high because it has a smaller diameter compared to that of a bigger tube with a larger diameter. Okay. And the other thing that you should know, that you should put in your head, is that both tubes have the same volume of water that has risen. But because of the difference in the capillary tube, in the diameter of the capillary tubes, that's why we have one rising more than the other. So the one with the smaller capillary tube rises more. The one with the larger diameter rises less. Okay, so that is for the liquids, and that was for attraction, and that's why it rises. And the other explanation you can give, water, because the other thing is that also water rises. So water rises. Okay, water rises. Okay, let me zoom in. Catherine, is it okay there? Water rises. Catherine, you can just pinch the screen of the phone. You can just pinch it if you are using a phone. You can just pinch the phone and then you zoom in. So water rises because of the adhesive what? Adhesive forces between the water and tube molecules. That is also the reason why water will rise in those two capillary tubes. So we should also write those two reasons. So, okay, so that is the one of attraction. Now we go and we look at the one of repulsion, and we shall call it a weak or a term. So liquids that fall, Part B, liquids that fall in a capillary tube, in brackets, repulsion. You can zoom in, just pinch. So we draw the diagram first. So I've drawn this diagram. This is not good. Okay, let me just do it like this. One is there and another one is here. Like that. Then I have my trough like this. Hey, you are not seeing, but you should draw it from the book there. Okay, Bridget, are you there? Bridget? Bridget?
Yes, teacher.
Hey, I wanted to hear your voice. I wanted to know whether you're there. Ah, this is dangerous. But it's okay. So which liquid is this? Ah, you have seen the diagram.
Mercury.
I know, Sean, you can see very fast.
That was power.
That was Pav.
Yes.
Okay. Pav has seen the answer. I thought it came from your head.
It came from my head.
Oh. Okay, good. So these are the capillary tubes. Capillary tubes. Okay. So what I'm saying that here, it is the cohesive force that is greater than the adhesive force. So the level of the liquid in the tube will be below the surface of the surrounding fluid. This is because the force of cohesion between the mercury molecules is greater than the force of adhesion between the glass and the liquid clings on itself. So here they are giving just an explanation or the observation. So if you like, you repeat this experiment and then you put these capillary tubes in mercury that is in a beaker. So what will you observe? You observe a bigger depression in a smaller capillary tube and a less depression in the larger tube. Okay, so that's what you will observe. So let us write the observation here. The observation is that we shall have a bigger depression, is observed a smaller capillary tube compared to a small depression of mercury in a large capillary tube. That we shall observe. And what's our explanation to that? So if they ask if you want to write something about it, you may not say observation, but you may just write this. This is what we see. A bigger depression is observed in this. Or there is a bigger depression in a small capillary tube, and there is a less depression in a bigger capillary tube. So you have explained the diagram. And then after you have talked about the diagram, and then after you explain what you have talked about or what you have written about the diagram, and then you explain it in terms of the cohesion force and the adhesive force. So you say that since cohesion force is greater than the adhesive force, comma, the level in a narrow tube so it is because here cohesion force is greater than the adhesion force. Remember, cohesion force is between molecules of mercury alone, but adhesion is between mercury and the glass. Since cohesion is greater than adhesion, that's why we shall have a fall or a depression of the level of the mercury within the tube. So since cohesion force is greater than the adhesion force, the level in the tube falls down below the surface of the liquid. The level of the liquid, and this liquid this time is mercury. The level of the liquid or mercury falls down below the surface of the surrounding what? Surrounding liquid or fluid. Let us say liquid. Surrounding liquid or fluid. Okay. Which one is the surrounding liquid? This is the surrounding liquid. This one here is the surrounding liquid. This one. Okay. And this one is the one that has fallen below. Why has it fallen below? It is because cohesion is greater than adhesion. For the other one, we saw why it rises. It is because adhesion is greater than cohesion. That's what you should note. It rises here because adhesion is greater than cohesion. But it falls here because cohesion is greater than adhesion. Are we together, members? Yes?
Yes.
Yes. So it is because the cohesion force between the mercury molecules, it is greater than, So you can say, and because the cohesion force between, writing this, the cohesion force between the mercury molecules, we're not seeing cohesion force between the mercury molecules is greater than the adhesion force between mercury and glass. Okay, between mercury and glass. Full stop. Therefore, and the liquid and mercury and liquid, and the liquid clings itself. What do they say, cling? What's the meaning of the word cling? It tends to be with itself. It's clinging with itself, not clinging with a glass, but it is clinging with its what? With itself, Okay. So lastly, let us look at that. Here they are saying, please note, the amount of elevation or depression in a liquid depends on the internal diameter or size in the tube. A liquid rises higher or sinks lower when the diameter is small. So if the diameter is small, the liquid will fall down deeper compared to the diameter that is big. If the diameter is small here, the liquid rises higher than the bigger diameter. So for the smaller diameter, the liquid will rise higher or it will fall deeper. Are we together? Members, are we together?
Yes.
Yes.
So we can write that note and we say note. So note, we can say note. The smaller the diameter of the tube, the smaller the diameter of the tube, the higher the liquid rises, or the deeper it does what? It falls. So if the diameter is very small, the liquid rises higher or it falls deeper. Are we together? Okay. Examples of capillary. So they're asking, where does capillarity take place? I've given you an example. Where do we have capillarity? Where does capillarity take place? So these are the examples. Are you seeing them? So water moving up in a straw. When you just put a straw in water, not sucking it, but you just put a straw in water, you see water rising in a straw. I wish I had a straw here. I would have demonstrated for you. And the other thing is water being absorbed by paper. It's Roman number 1. I'm writing these ones. We are going to add others, like 2. Okay? Yes?
Yes.
So water rising up in a straw or glass tube. That is an example of capillarity. 2, water being absorbed by what? By paper. Now, when you put a towel in water, that towel after some time, it will be what? It will be wet, isn't it? Movement of water in movement of water in plants. So water runs from the ground through the roots. Water is sucked by the roots, and water starts to move within the tree, but by the capillarity, by what we call capillarity. Blotting paper absorbing water, blotting paper absorbing liquids. There is what we call color chromatography. Have you ever heard of it? Sean?
Yes.
Do you know what we call color chromatography?
No.
Eh?
No.
For example, if you get black ink, you can separate black ink and you see other colors of ink. So they use what we call, that is the separation of colors, color chromatography. So they put it on a substance like a piece of paper, they pour it there, and then afterwards they pour a liquid there, and then it starts to move. Even these people, if you go for testing, let's say you are going for testing for malaria, testing for malaria, or testing for HIV, or testing for pregnancy, what and what. Those instruments have got papers in them, such that when they pour certain liquid, or they put your blood and they pour a liquid there. Now that liquid keeps on moving. So it moves because there is capillarity. That's why it will be absorbed. That means that material, it is an absorbent material. It can absorb a liquid due to capillarity. All right. So let me give you your assignment. It is unfortunate that my computer is not responding. Okay. So members, I think we can stop here for today. We can stop here for today. So next time when we meet, we shall look at another topic in physics. We shall go to heat, and we shall look at another topic. That is tomorrow, isn't it? Tomorrow we shall look at heat, and we finish heat. Is it okay? So have a good day and be blessed. And bye-bye.
We expect water to move downhill. After all, rain falls down from the sky and rivers flow downhill to the ocean. But water can move uphill too. I'll show you with